Let me share my screen here. Where did this go? Okay. Okay, so this is, we're going to delve in just a tiny bit more on sklearn, scikit-learn, which is, you know, what we use for kind of machine learning and whatnot. And I'm going to focus on this concept of cross-validation and train test split. Okay, so the idea in when you are trying to fit models, machine learning models especially, is that you want to know how well will what this method or this model, how will it perform on making predictions in future data. Okay, and generally in all of these problems you'll have data that comes in, and this is known as your training data. Okay, and so you know, you could think of a linear regression problem. You've got X and you've got Y, and you want to fit you know, basically some kind of line that that predicts the Y values based on the X values. And so what you can do is you can make your model more and more and more complicated. You can, maybe your data set has, say, several X variables, and you can make, you can use all of them. And if you do that, you will get very good performance on predicting the values that are in your training data. Okay, you might even be able to achieve zero or very small error if you fit a model to your thing. And you might say like, well, that sounds good. Why don't we always do that? Well, the problem is you might be doing something called overfitting. Overfitting is using attributes of the training data and assuming those kind of attributes and that relationship is something that holds in the general population, but it's not. So for example, if you collected a whole bunch of information about a whole bunch of people, and you are trying to predict, I don't know, let's say their score on an exam, right? So you've got a bunch of information about different students, and you got scores in for an exam. You might create a model that basically that maybe gets, if you have your training data and you've got the values, you can achieve 0% error if you say something like, if your name is Brian and your last name is I don't know, you know, Jones or something, then your exam score will be 97. Okay, and so, you know, obviously using names to make a prediction in will probably not generalize to the population, right? So it'll be like, if the name is Brian Jones, then we'll get a 97, and maybe that is actually correct in your training data, but then in the population there might be somebody else named Brian Jones who will not achieve the exact same score. Okay, probably test scores will be more related to other things like, you know, what is their homework score, or how much, you know, what is their attendance, what is their, you know, things that we would expect to be related to academic things. You know, how much time did they spend studying, what score did they get on the last exam, things like that. But you know, depending on your data set, you might say like, oh, I've got name information, and if I include that in my model, I can achieve 100% accuracy. So the one workaround, so there's a few ideas to avoid overfitting, and one workaround is to use is to split our data into training and testing data. Okay, so with train test split, what we are going to do is we are intentionally going to separate the available data into a training set and a testing set. And we are only allowed to look at the training data to set up our model, to figure out the coefficients to use, to figure out what variables to use, to figure out exactly how our model should be specified. We then, after we fit the model to the training data, we then see how well the model performs at predicting the test data. So the test data is available to us and we know the answers, right? We say these are the inputs and these are the answers for the test data, and we can compare how well our model performs at making the correct predictions on the test data. And we might have several competing models that we've tried out, and maybe the competing models both perform very well on the training data, but we can use the competing models and put them on the test data, and we can compare their performance there, okay? And so one of the functions available to us comes in scikit-learn, and it's all under this kind of this broad category of model selection. And there's something called train test split and cross-validation score, all right? So I'm introducing a lot of topics kind of at a very high level in this class. And if you've taken later classes like 102B or 101A, these might be familiar ideas. If you haven't taken them, and I'm fully aware that that might also be the case because this is a lower div stats 21, you know, feel free to ask your questions, and also don't hesitate, or don't also feel bad if everything doesn't fully make sense this first time around, okay? So what we're going to do is we're going to start off kind of with our x variables, all right? We're going to just kind of take some numbers, and then we've got kind of the output variables, and then so I've got, if we wanted to do regression, we've got numeric output y, and if you want to do classification, I've got kind of a categorical output z. All right, so this is what we're going to do, and I just kind of want to show this is not actually the data we're going to use, but I just want to show how train test split does. Okay, so what it's going to randomly do is it's here I do train test split on x. Okay, so x is this 6x2 matrix, 6 rows, 2 columns, and we're going to say the test size is 1/3. Okay, and then you give it kind of a random state, and this allows for reproducibility, right? And so the output of train test split is a tuple that we can unpack into x train and x test. And what this is going to do is it's going to produce basically 2 arrays, okay, which is basically an assortment, a random selection of some of these values, right? So here, out of the 6 rows, the test, it's selected 1/3 of them to be in the test set, okay? And so by random, with random state 1, it selected basically row index 2 and row index 1, okay? And so it selected out 2, 8, and 1, 7, okay? And then the other values, 0, 3, 4, and 5, which again, they're selected randomly, end up in the training set, okay? And you know, if I change random state, say random state 2, then we're going to get different values. But again, the 2 things, the train test, the x train and the x test, will make up the full x training data. Okay. When you use the random state, it will you can apply it also to the y data. Okay, so the y data is 0, 1, 2, 3, 4, 5. Okay, and it will also split the training, the corresponding training and testing, right? So here I said random state 1, and if here I'm saying random state, the same random state, it's going to split the y to match the x training and x test as well, okay? So x train has values 4035, which, you know, I intentionally made kind of this column be exactly equal to y, so you can see that they match it perfectly. So you can see 4035 gets selected, 4035, and 21 gets selected, and 21 gets selected in y, okay? And train test split actually allows you to do this simultaneously. So you don't have to split the x and split the y in 2 separate commands. You can actually give it both x and y, and it's going to split the full array into the exact same results, okay? And it's going to return a tuple of x split into train test and y split into train test, okay? And so, so here we get the exact same results that we have here, okay? 4035, 21, 4035, 21, okay? So we have, so we can apply it to the arrays simultaneously, all right? If you have, so let me just show you. So here, I'm going to do the same thing, okay, with Z, okay? And so Z is 0, 0, 0, and then 1, 1, 1, okay? And so if I do random state 1, okay, 4035 end up in the training, and 21 end up in the test, right? Unfortunately, as far as the Z variable is concerned, 4035, okay, it's rows 0, 1, and 2 have have class 0, and then 3, 4, and 5 have class 1. So just by random assignment, okay, when I split it this way using random state 1, all of the ones end up in the training set, and then the test set ends up all zeros, okay? And so, so that's generally not something that you want, okay? You don't want your test, you don't want to have a lot of imbalance in your training and your testing data. You don't want your training data to be like mostly ones and your test data to be mostly zeros. And so what you can do is there's an option called Stratify, okay? And Stratify will kind of make sure that the classifications, okay? So we're going to say Stratify using variable Z, and this will kind of ensure that the classifications are split appropriately. So here, when I say Stratify on Z, okay, then when it selects the rows, it selects 0, 4, 2, 5, okay, which makes sure that half in our training data, half are zeros and half are ones. I've got 2 zeros and 2 ones. And then similarly in our test data, it selects rows 1 and 3, which is half 0 and half 1, okay? And so if you're doing, if you're setting up a model with classification, you'll probably want to use this option Stratify so that your training and testing data will kind of be balanced as far as the classifications that appear, okay? And you know, if it can't balance it perfectly, it'll at least try to do its best job in balancing these things, okay? And again, the idea here is you want to create a model that will fit the training data well and perform well on the testing data. And it will help you avoid overfitting a model, meaning you find a model that, you know, predicts the training data very well, but performs poorly on the test data, okay? Because the test data is kind of like your practice on, you know, can you do something very well, right? It's kind of just like, you know, if you, when you're like studying for a test, okay, you know, maybe the professor will give you like a practice exam, right? And you might learn the practice exam material super well, okay, so that you can get 100% on the practice exam, okay? But if you've focused only on in learning the practice exam, or if you studied in such a way where it's almost just kind of like you've memorized the answers on the practice exam, right? You've memorized the answers are A, B, C, and D. The answers go A, D, C, E, rather than learning the concepts, but you just kind of memorize the multiple choice answers on the practice exam. When you're presented with new problems that did not appear in the practice exam, then having memorized the letter answers is not going to do. You're not going to get good performance, right? What you want is when you're studying the practice exam, you want hopefully your studying is going to be something that will generalize to new problems. And similarly, when you are setting up a model, you want a model that will generalize well to new problems and not just do well on the kind of the training examples that you have. All right, so here's just kind of an example that we can do, right? And so there is a very famous data set called the IRIS data set. And this has been around for a long time. This is, it actually is so famous, it gets its own Wikipedia entry, okay? And this is, this was data that Ronald Fisher used way back in 1936. And this was in this paper, Multiple Measurements in Taxonomic Problems, right? And he used it for linear discriminant analysis. And the idea here is that the input data is numeric. You've got four numeric variables, okay? And from the four numeric variables, you are able to predict the species of iris, okay? So we've got Setosa, Virginica, and Versicolor, okay? And this is what they look like. This is the Versicolor iris. This is the Virginica iris, and this is the Setosa iris, okay? And apparently what they did was they measured how long the petals are, how wide the petals are, how long the little what is it? The stamen, the sepals. Okay, so on a flower, they measured how long the sepal. Where is it? This thing. Okay, how long the sepals are, and to see. I don't know. So they got all these measurements, right? So you have sepal length and sepal width. So you have these four numeric variables, which works very well for all of our machine learning things, okay? And so, so anyway, the data is stored as a bunch in Python, which is like a dictionary that allows for different kind of data types. And so as far as the iris data itself goes, here are just kind of the first 8 rows. And we can see these are, this is one observation, and it consists of 4 numeric values, okay? And the feature names are sepal length, okay, sepal width, petal length, and petal width, okay? And these are the target values, okay? And these are categories. They are either zeros, ones, or twos, and we want to be able to predict. So the zeros are Setosas, the ones are Versicolor, and the twos are Virginica, okay? So this is based on these numbers, can we tell that this is going to be Setosa? And based on different numbers, can we tell it's Versicolor? And based on other numbers, can we tell it's Virginica? Okay. There's a full description of it, okay? There's 150 instances, 50 in each class, 4 numeric predictors, and this is what we have. And it's got some summary information here from Ronald Fisher way back in the 1930s, okay? So what I'm going to do is I'm going to split it using train test split into X train, X test, Y train, Y test, okay? And we're going to just, I've arbitrarily chosen 20% to be in our test cases, which is, I guess depending on the abundance of your data, you can choose a test size, probably recommended numbers somewhere between 10 and 20%. Sometimes people go higher, like 30%, but that's generally kind of what we do. And then we're going to use Stratify, iris.target, which is going to kind of ensure that in our training data, each of the three classes are equally represented. Okay, so because we have in the full data, we have 50 in each of three classes. And so when I split the, use iris target, it's going to make sure that we get, and we're going for 20%, it's going to make sure that in the test data, there's 10 of each class, and in the training data that there's 40 of each class. Okay? So we'll go ahead and do that, and we can kind of check, all right, what is the shape of the training data? The original data is 150 rows and 4 columns. Here we're keeping 20% or 30 rows. So that means our training data will have 120 rows and 4 columns, okay? And we can kind of count. We can do a bin count. And indeed, we have 10 of each class in the test data after we split the Y, okay? Because we did stratify equals iris.target. Now, if I got rid of that line, okay, we would, because the training data is 20%, we'll still have 120, but this will not be even. I will not necessarily get 10, 10, and 10. So here I get 11, 13, and 6, okay? So the Stratify option ensures that this will have 10 of each class in the test data, which is a desirable feature for us. All right, so there are different methods here, okay? And so I'm going to just show you some slides from my 102B class regarding the k-nearest neighbors classifier, okay? All right, this is not it. Sorry. Okay. So the way k-nearest neighbors works, okay, is that, so this is, let's say this is our training data, okay? In our training data, we have 3 classes, okay? But here's training k-nearest neighbors example when there's 2 classes. I've got red dots and I've got blue dots, okay? And the way k-nearest neighbors works is you've got a test case, okay? You have a test case. And when you run the k-nearest neighbors classifier, what the algorithm does, okay? So here I've got 2 classes in 2 dimensions. And technically in this thing, we've got 3 classes in 4 dimensions. The 4 dimensions are the 4 variables that we have. But conceptually, it generalizes, okay? The idea is, here's your test case. And we want to know, is this test case going to be a red dot or a blue dot, okay? And the way it works is you measure, from the test case, you measure the distance from the test case to every single other dot in your data set, okay? So we're going to take this test case and we go to every single other dot and we measure the distance. And then we say, all right, which dots are closest? Which dots are closest, okay? And visually, it's easy to see that like these dots are the closest, okay? But in higher dimensions, you actually, it's not easy to tell. You can't just visualize which dots are the closest. And so it requires that you actually do calculate the distance in high dimensions. And so anyway, you measure the distance to every single other dot, and you pick the k that's the closest. So you select some arbitrary k, maybe k equals 1 or k equals 5 or something like that. So if k equals 1, the nearest dot is red, and therefore this test case would get classified as red. If we chose k equals 3, okay, these are the 3 closest dots. I've drawn a circle to kind of show that these are the 3 closest dots. And out of the 3 closest dots, 2 are red and 1 is blue. Okay, and so because we have a 2 to 1, this is going to get classified as red. Okay, because we've got 2 red and 1 blue. Okay. However, if you go up to k equals 5, at k equals 5, out of the 5 closest dots, 3 are blue and 2 are red. 3 are blue and 2 are red. And so in that instance, this test case would get classified as blue, okay? And if you go up to k equals 7, okay? So these are the 7 closest dots. This is not, this one is just a tiny bit farther away than this one. So out of the 7 closest dots, 4 are blue and 3 are red. And so because you've got 4 blue versus 3 red, it's going to get classified as blue, okay? So how this point gets classified, either as red or blue, depends on the k that you've chosen, okay? I've got another example where here's the test case, okay? And this one seems a little bit more clear that it should be red. And again, the idea is you measure the distance to every single other data point in the data set, and you're going to pick the closest one. So the closest one is red, it gets red. Here are the 3 closest. 2 are red, 1 is blue. It's going to go red because we got 2 red, 2 over 1. Here we have, here are the 5 closest, and out of the 5, 3 are red and 2 are blue. So 3 versus 2, 3 are red, it's going to go red, okay? Here's 7, we've got 4 red and 3 blue, it's still going to be red, okay? So that's kind of how the k nearest neighbors works, and it generalizes into higher dimensions. You just kind of have to find the distance in 4 dimensions, which is difficult for us to picture, but that's what the k nearest neighbors classifier does, okay? And it does that very quickly in scikit-learn for us, okay? So, so here's, I'm going to just load a couple things for visualizations, okay? And I'm going to make a data frame out of our X training data, and I'm going to add a column for species, okay? And so here is our training data and the labeled species. And so we didn't cover seaborn, but there's a plot called a pair plot that allows you to kind of visualize the data set here, okay? So this is, if you plot, I guess I should have labeled, okay. So let me label the columns as iris.feature names, and then let's make the pair plot again. Okay, so you know, we've got 4 numeric variables, and so if you plot supple length and supple width, those 2 variables, this is kind of what the plot looks like colored by dots. If you plot supple length and petal length, this is what you have. Supple length and petal width, this is what you have, and things like that. And so you get, you know, there's some clear relationships, and you know, based on petal length and petal width, we can start to kind of draw, you know, locations. But again, the data exists in 4 dimensions, and so we would have to kind of figure out the distance in 4 dimensions. So it's already 2:40. So I'm going to just kind of set up the k-neighbors classifier. So I imported the K-neighbors classifier way back here under sklearn.neighbors, right? And so all of this stuff, you know, if you forget, right, you can just say, how do I say scikit-learn K nearest neighbors, right? And you can kind of just look for the help, right? So usually the kind of the first thing we got sklearn neighbors, K-neighbors classifier, and then this is kind of the module that kind of explains it. So this is the function itself that describes this is the documentation for the function, and here is kind of a little tutorial that will walk you through it, okay? So anyway, I set up the K-neighbors classifier, and again, it's just going to be a model object, and so we are going to fit it to the training data, and this is all you have to do. knn.fit on the training data, the ytrain, xtrain, ytrain. And then now that we fit the data, we can say, all right, make predictions on the test data, okay? And this is what it predicts. It predicts 201002222, okay, based on the data, right? We can compare the test predictions, the predictions on the test data to the actual y-test data, right? And so we go, oh, what, it predicted 2 and the actual value is 2. Predicted 0 and the actual value is 0, right? So it looks like it's doing pretty good, okay? And we can see, you know, if you look line by line, you go, oh, here's a mistake. It predicted 1, but the actual value is 2, right? Are there any other mistakes that it made? Okay. It doesn't look like it, but rather than having to go through it entry by entry, there's something called a confusion matrix, okay? The confusion matrix, ideally you get things down the diagonal. Ideally when the actual case is 1 and the real value is predicted value, the predicted value will be 1. But the confusion matrix, okay, is under the metrics portion. You're going to do sklearn metrics, import confusion matrix. You're going to take the confusion matrix and you're going to compare the actual values, y-test, to the predictions made on the x values. Okay. And this is what we get. So this is when the actual value is 1, or 0, we predicted 0 10 times. When the actual value is 1, we predicted 1 10 times, right? And here, this is the actual. The actual is 2, okay? And 9 times we predicted 2, but 1 time we predicted 1, and we can see that, right? So 1 time we predicted 1, but the actual value is 2. And so, so this is our accuracy, is we got it right 29 out of 30. Okay, that's our that's the accuracy rate. Okay, we can compare. So this was k nearest neighbors using 5 nearest neighbors. Okay, and we can see. All right, how will it perform if I use just the 1 nearest neighbor? Okay, so the 1 nearest neighbor, we actually get the same performance. So here, knn1. This is how easy it is. You just say, create a k-nearest neighbors classifier when the number of neighbors is 1, fit it to the training data, and then let's go ahead and make predictions here. And then let's compare predictions to the actual values, and here's our confusion matrix. So this is what we have. Here's another KNN model. We're using 25 nearest neighbors. Okay, we get xtrain, ytrain. And then we're going to compare the actual y-test values to the predictions using the 25 k nearest neighbors, okay? And so when we do that, it performs less well, okay? We get, we've made 2 mistakes here. Okay. And so there's a tool called grid search CV, right? So you might say, well, I want to try out 1 nearest neighbor and 5 nearest neighbors. So what we did is manually we've done 5 nearest neighbors, 1 nearest neighbor, 25 nearest neighbors, right? And so these are different options you can specify when trying out your k nearest neighbors. And so one thing you can do is you can do something called grid search, and we can say you know what? I want you to try out using 1, 2, 3, 4, 5, 6, 7. I want you to try out all a whole bunch of different nearest neighbor things, okay? And so what we're going to do is we are going to say, this is the grid of parameters you want to try as far as nearest neighbors, which is this argument. So we're going to take the argument and put it in the dictionary. So this this has to be the name that we're going to use, okay? That's what we'll use. And then there's another thing, as far as k-nearest neighbors goes, there's another argument that that you can use called weights. Okay, weights is can be either uniform or distance. All right, and so when we were talking about this, we basically we said we get 4 red versus 3 blue. Okay, and so when you counted up kind of the votes as to whether this classification point, test point, should be classified as red or blue, we said it was 4 red versus 3 blue. What a weighted k-nearest neighbors model does is it says, hey, you know what, let's look at the distances for each of these points. And the closer points, their votes count more. And the farther points, their votes count less, okay? And so sometimes that can affect how it might go, right? So for example, in this case, we'd say, all right, which points are the closest, right? So this one went blue because it was 4 blue versus 3 red. But in a weighted model, we would say, you know, these 2 points, which are red, they count more. They count more, okay? Their votes count more. And the points that are farther away, their votes count less, right? You know, it's a little bit less democratic, but it's the idea that the ones that are closer, their votes should count more. And so that's, you can do a uniform or distance-based weighting, okay? So anyway, we're gonna do, set up the k-nearest neighbors classifier, and then you run grid search, okay? And what grid search will do is it's gonna run the k-neighbors classifier, and it's gonna try out all of these different parameters for us. It's gonna try it out for nearest neighbors 1, nearest neighbors 2, nearest neighbors 3, all the way up to nearest neighbors 50. And it's also gonna try weights uniform versus weights distance. So it's gonna have a whole bunch of different models that it's gonna run. And it's going to do cross-validation. Cross-validation is similar to a train test split, but it will automatically kind of reevaluate the models. It will perform 5 different train test splits. And so, so we'll run this, and depending on your grid search, it can take a long time or it can be very quick. In our case, it was very quick. But if you have a very complicated model with a whole bunch of different, if your parameter grid is very big, this can take a long time, okay? And so, so this is, it's done now, okay? And we can say, all right, what were the best parameters? And it said nearest neighbors 13 using uniform weights. What was the best score? 98. So actually, this is the best performance it got, which was for the training data. It made 2 errors out of, for the training data, there were 120 cases. It made 2 mistakes out of 120. So it has an accuracy of 98%, and that's where this k-nearest neighbors cross-validation best score comes from, okay? And we can see how well does it perform on the test case, and it still makes 1 mistake, but this was apparently the best performance it got when it tried out all of these different models. And we can see this is its actual cross-validation score, which is when we ran it for this, basically it splits the data into several different chunks, and in some cases it was 100% accurate, and in other cases it made a mistake, one out of 1 out of I don't remember, 30 or something. So it made a mistake. And so this is kind of the accuracy. And if you average all of these together, you get, this is what you end up getting, 2 out of 120 there. Okay. I did something similar with a naive Bayes classifier. We're running out of time, so I'm not going to bother going into it right now. But that's what we'll have today. I'm not going to give you an assignment. I'm not going to test you on this kind of stuff, but this is just kind of like, if you're interested in like some basic machine learning ideas and you want to get started with sklearn, there is a lot of resources out there, okay, that you can kind of read any of these modules. And the documentation in sklearn is also, it's very well documented. There's lots of good examples. And you know, anytime you get started on something, it can be overwhelming. But just like anything else, the more you try it out and the more you practice, the better you will become at learning those things. All right, we'll wrap it up here for today, and you know, we'll take it easy the rest of the week. I guess on Wednesday I'll kind of cover what you can at least expect for the final. Again, it'll be I'm going to be pulling questions from HackerRank's pool. No quiz today. I'm going to just kind of make the this last week, week 10, the lectures will be optional, and I won't put we won't have online quizzes for this final week of class here. So so thanks for tuning in. I hope you are not disappointed that there's no quiz today, but I appreciate you guys tuning in, and we will see you guys on Wednesday. So we'll end there.